So I haven't got as long as I'd hoped to talk about space-time wormholes. So let's, maybe I'll get to the points that are important for the questions that everyone was just asking. Okay, so what is a space-time wormhole, first of all? It's a shortcut between distant points of space-time. So we have some points.
Henry, I think you have 45 minutes still, so we started a bit later, so that's
fine.
Okay.
Thanks. I was hoping to have an hour, but thank you. Okay, yeah, so a space-time wormhole is that we have some points in space-time. So this is a picture of space-time, let's emphasize, not a picture of space, where there are some points that are very well separated in space or in time, and we can take their separation to be as large as we like. So we take their separation to infinity, but there's some in the sort of ambient space, but there's some shortcut, some wormhole that has some constant length and constant geometry as we take the separation in the ambient space to infinity. So, you know, if we really take this limit, we can think of X and Y as living in some completely different universes. So this maps exactly what what we had before. So in this limit, it becomes, we can actually have disconnected boundary conditions for whatever calculation we're doing, but a connected space-time. So we have a picture like this, and in fact, our replica wormholes that we just saw are examples of this, where we have disconnected boundaries, but connected geometry. And these look like there might be a problem because they mediate some kind of non-local correlation in space-time. And this is something that was discussed a lot in the 80s, and we're sort of in the early 90s, and we're reviving it in a slightly different context today. Just a picture of what's going on in space. So you can imagine maybe in this picture, maybe time is running in this direction. So you can think of this as a process where you start with just an empty ambient, that's really not the time machine. But anyway, yeah, okay. We can think of this process as having these empty ambient universes, and then at some point in space and some point in time, there's like a tunneling process that produces some little closed universe. And that little closed universe sort of exists and then propagates and then arrives at this, this other separate universe. This is one way of thinking about these space-time wormholes, is that they're describing a picture where this small baby universe gets exchanged between parent universes. So that's one way of thinking about them. And we'll talk a little bit about the Hilbert space associated with these closed universes. So this is useful for a Hilbert space interpretation. And I'll just quickly note that these things are not the same as spatial wormholes, something like the Einstein-Rosen bridge, which are eternal in time and are shortcuts in space. These are shortcuts in space-time. So they're localized both in space and in time. So these give us some correlations that are non-local in space-time, whereas the spatial wormholes give us correlations that are non-local in space, but that's something we're actually sort of very familiar with. It's sort of geometrization of quantum entanglement. But I just want to avoid confusion, these spatial wormholes are not the same thing we're talking about. Yeah. Okay, so we're going to sort of take a bit of a abstract way of thinking about the gravitational path integral to try to understand what these things can do in general. So it really seems like we might be breaking sort of cluster decomposition, for example, precise notions of locality that say that experiments in one universe and experiments in another universe shouldn't be correlated, or the correlations should decay with as we take things to be very, very far apart. It looks like these wormholes could interfere with that. So to understand whether that's possible, I'm going to take a sort of slightly abstract way of thinking about things. So we're going to think about a gravitational theory as a map that gives you amplitudes as a function of boundary conditions. So you decide on some set of boundary conditions. So maybe M is some boundary condition. Again, I'm being a little bit sort of general. And we can then compute the path integral where the boundary conditions for our fields are fixed. And then this gives us a number. So very abstractly, we can think about it like this. This could be the sort of gravitational path integral we've been talking about, or it could be something more, some string theory or some UV thing. It doesn't really matter what this theory is. It just matters that it's taking some boundary conditions and computing a number. So ADS-CFT here is an example, and we'll use that as a kind of a crutch for our language and our way of thinking, where this M you should think of as being a d-dimensional spatial manifold, sorry, a d-dimensional manifold, and you could also include a metric and sources for some operators, if you like. And then the boundary conditions for ADS-CFT tell us that we have some ADS, d plus one-dimensional ADS spacetime that asymptotes to M at infinity. And the sources tell us how the fields fall off. So this data tells us about some boundary conditions. And then what this amplitude computes is the partition function for some CFT that lives on this manifold with these sources turned on. So that's what we'll sort of have in mind. So okay, and this includes, by turning on sources, you can compute correlation functions and all the rest of it. So this is really the most general. This is really some very general object. But now these space-time wormholes, this is a precise version of this problem that they seem to give us non-local correlations. That you could have a path integral that has two disjoint boundary components. And if you take this gravitational amplitude with, sort of do a gravitational path integral with two boundary components, then you might sum over geometries like this. So we've got some boundaries M1 and M2. You could sum over geometries that don't connect them, but you could also sum over geometries that do connect them. So this is a space-time wormhole. But if you just computed the two things separately, you computed, first of all, the amplitude with boundary M1 and amplitude with boundary M2, then these are two separate calculations. You don't get any wormholes that connect them. You could think about them as the first one is computing a path integral over pink spacetimes, and the second one a path integral over blue spacetimes. They just they don't talk to each other. And these things, at least they don't look like they're equal. These wormholes look like they'll spoil this. Okay, so in terms of gravitational physics, this seems like it might be a problem for locality. We could think about M1 and M2. I've abstracted them away as being actual asymptotic boundaries, but they could just be different sort of weakly gravitating regions that are very, very well separated. And it looks like these different regions are becoming correlated by these wormholes. And it looks like it might sort of destroy locality of interactions. But it's also sort of more, in this context, is certainly a problem for the usual way we think about ADS-CFT, because these two things should certainly be equal. If you have a local quantum field theory, then the partition function on a disconnected manifold is given by the product of partition functions on the components. So this seems like a problem. What we'd like to know is how bad the problem is. And the answer is it's not as bad as you might think. Yeah, so we're basically going to be asking what form can these space-time wormholes induce some sort of correlations, but what form can those correlations take? And they take a very special form. So a useful way to think about that is to talk about this Hilbert space of baby universes. So to warm up, we're going to start off by talking about Hilbert spaces in quantum field theory in general, and then we're going to apply that to gravity. So in quantum field theory, a Hilbert space is associated to a spatial manifold. So the idea is that you have some, maybe you're computing some some amplitude, you have some initial state, you have some final states, and you want to, maybe you've got some operators that are inserted. Then a Hilbert space, you ask about the intermediate states that propagate along some spatial slice sigma. So you have some intermediate states. And they live in a Hilbert space that depends on the geometry of this spatial manifold sigma. And perhaps if there are sources turned on and so forth. But let's just say the geometry of that manifold sigma. So quantum field theory, so every possible spatial manifold associates a Hilbert space. So in the context of our ADS-CFT, these would be D-1 dimensional manifolds, codimension 1 manifolds. And if you have then a manifold with boundary, something like M minus, then this actually defines a state. So in our picture over here, this lower half here is defining M minus. It's a manifold with boundary with some sources inserted. And the idea is that we produce a state by doing the path integral on M minus. So this defines us some state in H sigma, where sigma is the boundary of our space. So this is D-dimensional. So just simple examples of this, if you take sigma to be a disjoint union of two spheres, one possible manifold with boundary is two half cylinders, and this produces the vacuum state, or two copies of the vacuum state. You're doing evolution for infinite Euclidean time. This is Euclidean cylinders. So this is a definition of the vacuum state. Another example is you take this cylinder to connect the two. So the sphere times an interval, and this produces a thermal field double state. And of course, you could always insert sources. So you could produce primary states in a CFT, for example, by taking a manifold that's sphere with a source inserted, for example. Okay. So this is sort of a very general abstract way to think about what a Hilbert space is doing. Then to compute the inner product, well, we do this picture up here. We take the state that's defined in the lower half and the state that's defined in the upper half, M minus and M plus, and we just create the manifold by gluing these two guys together. And then once we've glued these two guys together, we compute the path integral, or the partition function of the theory on that composite manifold where we've glued them together. Okay, one of them has to be CPT conjugated, but that's a sort of minor detail for us. So for example, if you take two of these thermal field double states, you glue together two cylinders along their common boundary, and you get a torus. And then that computes the thermal partition. Okay. Yeah, so this is a way that people talk about this in particular in topological quantum field theory. It's a very natural way of talking about it, where these manifolds are really just topological manifolds. So this is the sort of ingredients that go into the Atiyah axioms, for example, for TQFT. But this kind of discussion in generality is how we construct, is one way to think about Hilbert spaces in quantum field theory. Okay. That's why so we're going to do precisely the same thing now in our gravitational theories, except we're just interpreting these manifolds slightly differently. We're interpreting them now as some boundary conditions or partial boundary conditions. And then this inner product is going to be between two partial boundary conditions. Is you take the partial boundary conditions and you sew them together into a complete boundary condition, M plus M minus, and you compute the path integral with those. But in particular, we're not going to there are very natural things to insist on in quantum field theory. The amplitudes, partition functions factorize, and the Hilbert space on a disjoint union of two manifolds is a product of the Hilbert spaces on the components. So these are natural things to demand of local quantum field theory. We're not going to insist on these. Okay. If we don't insist on that, then it means that there's one sort of canonical Hilbert space that's interesting. And that Hilbert space is is where this spatial manifold is just empty, is that we don't have, yeah, so maybe I'll just say for this, we think of H of sigma is equal to the Hilbert space of say universes with asymptotic spatial boundary sigma. That's the idea. So here, sigma was this, in the quantum field theory context, sigma was the space the QFT lived on. Here, because the geometry itself is dynamical, sigma is going to be just the boundary of the spatial geometry. Instead, the bulk of the spatial geometry is something that can fluctuate and is that depends on the dynamics. So one of these examples is where the universe doesn't have a boundary. So this is closed universes, universes. And for us, we're going to call this the baby universe Hilbert space. Because it's going to be telling us about these exchanges from space-time wormholes. And in that case, our partial boundary conditions just become the complete boundary conditions again. So here's a picture of what's going on as you have some boundary manifold M1 and some other boundary manifold M2, which in this case I've chosen to be disconnected. And then to compute the inner product, you integrate over all possible spacetimes that connect these things all together. In other words, you compute this this sort of gravitational path integral where you take boundary 1 and boundary 2, and you just take the union. Okay, slightly abstract construction. So do ask if there are any, if anything needs to be clarified. Maybe I can fit it all on the slide. Okay.
So the in QFT it's codimension 1 and gravity is codimension 2.
Yeah. So that's so let's say, let's just fix things. We'll say that the boundary or the space-time on which QFT lives is going to be d-dimensional. The gravitational theory is going to be, so this is something like M is d-dimensional. The gravitational theory is d plus 1 dimensional. I guess I haven't given a name to the bulk manifold, but. And then sigma is d minus 1 dimensional.
Okay, good, thanks.
Yeah. Right. Yeah, so maybe, well, do I want to? Yeah, so maybe I'll just, let's say that in this 2-dimensional example, so we were talking about 2D gravity, so something like JT, then the bulk manifold, this is a case d equals 1. So bulk manifold, well, what do I want to say? Then, so a manifold M might be something like a union of circles. So it's S1 times S1 beta 2, etc. So this would be a picture of M, of some particular M. And sigma would be a collection of, just a collection of points. Okay, strictly these are oriented, so the collections of points would be points with signs. So this is a zero manifold. And then the dual theory is a quantum mechanics. So yeah, the dual theory is a quantum mechanics. So it just has so there's no space in the dual theory. There's only a time direction. I don't know if I can answer it. Okay. So with that kind of abstract notion of what a Hilbert space is, we can now completely construct, for example, this baby universe Hilbert space or all the others. And here's the basic idea. First of all, any manifolds, any closed manifolds that give you boundary conditions correspond to operators. And here's a definition. It's something very simple. You take your manifold and it can act on any state. And the way it acts on that state is just by appending this extra boundary. So the picture is something like this. You start with a state that's defined by this boundary M2, and maybe you have some universe that's produced from this boundary. So this defines some state M2, and then you throw in another boundary. You say, okay, there's going to be another boundary M1, and that produces some other universe, and they might interact, and there's some new state that involves both of them. So you get this new operator that's defined by introducing an extra boundary. But these operators have a very simple algebra. In particular, it's an abelian algebra. They all commute with each other. And there's a more technical point about adjoints, but important, but not the main point for today. So we have this abelian algebra of operators defined by inserting algebras. We also define by inserting boundaries. Sorry, there's also a very special state here, the no boundary state, and that's the state defined by the absence of any boundaries. So this is like the Hardle-Hawking no boundary state for cosmology, for example. So it's just one of the possibilities here is that M2 is empty, and this universe was spontaneously created out from the vacuum. So this is just some closed universe. So our initial state here was the no boundary state. Okay, and we're actually going to define our Hilbert space by saying that you get to all states like this. So you start with a no boundary state and you throw in a load of boundaries. So you act with these operators to produce more and more boundaries, and this produces the state M1 disjoint union M2 disjoint union up to Mn. And we're just going to say that these are all the states of our baby universe Hilbert space. This is a definition essentially. So that there could be in principle other states of closed universes, but they're never produced in these sorts of by boundaries, so they don't actually play any role in these spacetime wormholes. So in particular, it means that we can now compute any partition function, any one of these gravitational amplitudes, we can write it as a matrix element like this. So you start with a no boundary state and you insert a load of these operators and you take the expectation value in this no boundary state. And now the important thing about these properties, that these operators are commuting and they're complete in this sense, means that they basically build the whole Hilbert space for us. They're like the Hamiltonian and the angular momentum operator in a hydrogen atom. They're a complete set of commuting observables that we can diagonalize, and then the simultaneous eigenstates, once we diagonalize them, span the Hilbert space. There's some orthonormal basis alpha where inserting a boundary just gives us a number. This is sort of an abstract consequence of these properties. Okay.
So this postulates, these are assumptions, or?
Okay, so there's, I'm defining a gravitational theory as,
okay.
Maybe I didn't in this, defining a gravitational theory as being something that takes boundary conditions and gives you amplitudes.
Yeah.
Then most of this construction is then sort of inherent in that, it's just the fact that we've got this fact that boundary conditions are, you can always take the disjoint union of boundary conditions. This is a sort of postulate. It's a relatively weak axiom. There is a, I have to tell you what this CPT conjugation operation is. So that's a choice that I have to make again. And then I'm really making one assumption that is not sort of obvious, that's very strange. And that's the fact that you actually build a positive definite Hilbert space out of this, that this makes sense as a quantum mechanics. So I guess I didn't write it down anywhere at the moment, But yeah, okay, I should emphasize that there is one key assumption here, which is that the Hilbert space you build like this has a positive definite inner product. And so that basically says that there really is a quantum mechanics describing closed universes, and not, you know, something strange that has a inner product with negative norm states. And that's totally not obvious from the starting point, but it's sort of a consistency condition. Something we'd expect of a sensible theory of quantum gravity, I would say. It's not obvious, but it's very natural to demand.
Question. So the states alpha are not very geometrical, are they?
No, so typically alpha is going to be some extremely complicated, maybe it'll have a bit of the no boundary state in it, and it'll have some states with some single manifolds and some other states with M1, M2, and it'll be some very complicated combination of things like this. So it'll be a superposition of all sorts of possibilities. And in fact, in examples, it's kind of these states that you don't really have control over them in because the higher topologies don't tend to be suppressed, but that's a minor point. So there's a question in the chat, which is whether alpha are like coherent states. Is actually a better way of thinking about this is think of these M hat operators as being a bit like position operators. So the one way of thinking about that is that they can create a universe, but they can also destroy a universe. And they have amplitudes of doing both, or destroy an anti-universe. Okay, they should come with some labels, but so they should think about them more like a position operator, and then alpha is like a position eigenstate.
Can I ask one follow-up question? So if it's like a position operator, then should I be worried if alpha is kind of like a normalizable in the usual sense? Because if it's really a position operator, it's delta function normalizable, not the...
Yeah, that's what, yeah. So it will probably have some continuum normalization. So yeah, but there'll be... but there's still a there's still a formal completeness relation. There's going to be some measure d mu alpha alpha. Okay, so they don't, if they're continuum normalized, then they don't live in the Hilbert space strictly, but they still exist and have a rigorous life. But it's they're the usual position or momentum eigenstates. So we have, in examples, something like JT gravity, then yes, these are sort of continuum delta function normalized. Yeah, so I'm going to write everything as discrete sums over alpha, but you should bear in mind that really it'll include some continuum integral for exactly that reason. Okay, so let's go back to our calculation of the partition function. It's some matrix elements of boundaries, and now we can insert a complete set of these simultaneous eigenstates. Okay, this is just the completeness relation, inserting the identity. And now, because these MNs are all just hit alpha, you just get eigenvalues, then you end up with a very simple formula like this, where you have some weightings that come from just the overlap of the no boundary state with any particular alpha state, and you get a norm squared. So in particular, under the assumption that we get a positive inner product, these weights are positive, and they all sum to 1 if the no boundary state was originally normalized. And then they're weighted by these eigenvalues. So what this is telling us is that these manifolds, we could potentially introduce correlations between these different boundaries, but they all take this form of classical correlations. So they take a very specific form this is just saying that we have quantum mechanics, but we only have access to some commuting set of operators, and quantum mechanics with commuting operators just becomes regular probability. It's like you don't need the phases in the wave function. You only need to know the modulus squared of the wave function in the alpha basis. Okay, so this this is an abstract version of something that people talked about in the 80s. In that case, these wormholes were leading to, for example, random correlations between parameters in the Lagrangian. So it looks like you're going to have correlations at very, very long distances, and indeed you do. But all it is a classical. It turns into a classical distribution for the value of those parameters. So, for example, people were talking about the cosmological constant a lot. It leads to a random cosmological constant, which is a particular type of correlation that's there at long range, but a very special kind that that doesn't sort of materially affect the usual locality of physics that we know and love, in cluster decomposition. Okay, but it suggests there's this generalization of ADS-CFT now. Is if we take this seriously, again, our mantra for this course is to just look at the gravitational path integral and take it seriously and see what it tells us. And it says that we should that we get an answer something like this. Okay, this is what we just wrote down. So the left-hand side is our gravitational path integral with n boundaries, and now we can't interpret it as just a CFT partition function anymore. But if we were to fix alpha, then everything factorizes. So for fixed alpha, we get factorization. So the suggestion is that alpha is some label for not just a single dual CFT, but a collection, some collection of dual CFTs. They have some weights, and then we get partition functions for each CFT with some weighting. Getting there by this path of baby universes emphasizes an important point, which is that this, on the left-hand side, it looks like it only depends on the theory, but really we made some implicit choice when we did this gravitational path integral of an initial state of closed universes. And it plays an important role because it's telling us what the weightings are. And we could change these weightings within the same gravitational theory by choosing a different initial state of closed universes. Okay. All right, so we should get on to the questions people asked and interpreting this for the replica wormholes. Apologize if this is a little bit too quick, but the important thing going forward is going to be this relation essentially, is that we get classical correlations between boundaries. Okay, so let's talk about these replica wormholes. As we said before, this computation of the density matrix of Hawking radiation we can think of as being a particular boundary condition. It's one of our M's. One of our M's is the boundary condition that computes the density matrix. And this is what we would naturally do in, this is a generalization of very natural boundary conditions that we would, so in, yeah, I guess I've said these words on a previous talk, but okay. So these are the boundary conditions that we're going to use to compute the entropy of the state. We have our non-gravitational system where our matter theory lives over here. And we're going to make this cut where we insert some particular states. We're going to want to compute the density matrix of radiation, sandwich between these states. And this defines our boundary condition, and then gravity can do anything it likes in the middle. So just as before, this gives us the boundary condition, so it gives us an associated operator on the baby universe of Hilbert spaces. And we can go to these alpha eigenstates where these operators, rho ij hat, have eigenvalues rho ij of alpha. Right. Okay. so this density matrix is one example of these boundary inserting operators. So let's start off with doing a single replica calculation and interpret what that does. So this is basically computing the density matrix that Hawking calculated, say. And this is the result that we expect is essentially thermal and doesn't have the page curve. The entropy increases for all time. And it's interpreted this thing on the right-hand side is we can write it as a sum over alpha of these different sectors. But now let's do an n replica calculation. The important thing is we get essentially the same result, except there's not a separate sum over alpha for each question, for each replica. There's a single sum over alpha. So another way of writing that without all the indices. I don't like indices when I don't need them. So it's given by a tensor product, an n-fold tensor product of uncorrelated states, rho of alpha, but all weighted by p alpha. So this gives you a particular correlation between different copies. So in particular, it is not equal to this state. So this state would have n separate sums over different alphas. So in other words, if you create two identical black holes, called initial black holes, if we produce them in extremely well separated parts of the universe and we collect their Hawking radiation, then this is suggesting that in the presence of wormholes, these things have correlated Hawking radiation. Okay, how long do I have to wrap up?
I would say 5 minutes.
5 minutes. Good. Okay, so let's calculate some entropies and get this page curve. So let's take first of all compute the entropy without wormholes. So this is the sort of first calculation we did. We just took Hawking's state and we computed the entropy. So we can write it as an entropy of a sum over p alpha rho alpha. So if we were to do this using a replica type calculation, where we don't include the wormholes, then we're going to take the trace of this, the n power of this density matrix. And when we do that, we get this trace that includes n separate sums over alpha. So just using the formula. And just as a simple example, we'll take these different rho alpha to be all pure states, but all orthogonal to one another. Just as a simple example to contrast the two possibilities. Then these traces, if these rho alphas are all pure states, they're all orthogonal, we get 1 in the case when all alphas are equal, and we get 0 otherwise. So we just get p alpha to the end with a single sum of alpha. And so if you take the n goes to 1 limit of this, what you recover is this Shannon entropy of the p alphas. And this is what we can think about this as doing is quantifying how much entanglement we have with these baby universes. In this case, a baby universe is, you can think of as the interior of a black hole. Now, of course, sum over alpha, p alpha rho alpha is, I guess, yeah, so change my notation. Well, okay. This sum you can think of as you take many different, this kind of ensemble CFT interpretation. Rho alpha tells you about what the state of Hawking radiation would be in any particular theory, and we're taking an average. And I'll just denote that average by a bar. What we're computing is the von Neumann entropy of the average state. Let's contrast that with including wormholes now. So that means we're taking our n copy state, so we're producing n separate black holes, and we're asking about the expectation value of this permutation operator that we introduced before, this sort of swap test type thing. And rho n here is our n copy state where they're all correlated. So we're producing n black holes with correlated Hawking radiation, so we get a single sum over alpha, not a separate sum. And that sum over alpha factorizes out, and we end up with a sum that now looks like this, with a single sum over alpha. For example, taking our pure states, this trace of rho alpha to the n is just 1. It's just the nth variable of your state. And the answer, then you sum over all the alphas and you just get 1. So in other words, that gives us 0 gravitational entropy. So here we had this Shannon entropy. Here we've got 0. So what this is doing instead is computing the, instead of first of all averaging over all the different alpha sectors and then computing the entropy, we're first of all computing the entropy within each sector, and then we're averaging. So they're just two different calculations. And this now explains, it gives a coherent picture of what the difference is between these two calculations where everything is self-consistent. So this first one, without wormholes, is in some sense the correct von Neumann entropy. It's really what the sort of the right answer is in some technical sense, but it's completely unobservable. There's no in principle way to actually ever see this von Neumann entropy. And the reason is that if you were to, you can never see a von Neumann entropy, determine a von Neumann entropy from a single experiment. You have to learn about it by doing repeated experiments on many copies of the state. But if you do repeated calculations on many copies of the state, then all of your experiments end up getting connected by wormholes and inducing correlations, and you end up being sensitive to this second one. This which is the entropy within a given alpha sector. And this gives you a page curve. And in fact, okay. And this is the physical one. This is the one that you would really predict if you were to go and you had a very, very sophisticated experimental physicist who wanted to go and actually check what the entropy was from some black holes. And he went and did very sophisticated experiments forming many, many identical pure state black holes and collecting the radiation and doing various measurements, doing swap tests on them and so forth. Then he would come back and tell you about this answer, not this answer. Okay, so this is my last slide page, is to wrap up and give you a picture of the where we've arrived by taking this gravitational path integral extremely seriously. So first of all, the suggestion is that we end up with these super selection sectors for asymptotic observers. So super selection sectors is something that we may be familiar with from quantum field theory and so forth, is when you don't have access to the full operator of algebras that is the complete set of operators on your Hilbert space, then your theory has super selection sectors. So examples of this are when you have spontaneous breaking of a global symmetry in quantum field theory, or on a spin chain, then you can end up with super selection sectors. So this is something we're kind of familiar with, where there's some uncertainty about which sector you're in. And it's a classical uncertainty. So this introduces some classical notion of randomness. And we started with a single unique theory of gravity, and this theory makes some unique predictions. It's just that those predictions depend on what the initial state of the universe you chose was. And in particular, even though we're doing something like these black hole calculations, maybe in asymptotically ADS space, you still need to tell me what the closed universes look like, because those closed universes might come in and infect my calculation. And yeah, so this unique theory of gravity nonetheless seems to give us this ensemble for boundary theory, or an ensemble for asymptotic observers. The reason why you get this ensemble, or this sort of classical uncertainty, is because there's this inherently unobservable part of the system. So you're entangled with here the baby universes. But if there's some system you're entangled with and you can never directly measure it, then you might as well trace it out, and tracing it out leaves you with some classical uncertainty in your predictions. And then if you're actually doing experiments and making observations, what you determine is basically you determine which alpha you live in, and then you produce many copies of rho alpha. This is so it means that all your measurements are going to be compatible not with this superposition or mixture of different rho alphas, but rather a single rho alpha in the end. And all of these rho alphas, for example, we expect to follow a page curve. So superpositions like this are unobservable. The phases are completely unobservable, and the probabilities, the weightings, only tell you how likely it is that you're going to determine any particular sector. So I'm now going to leave you with a puzzle, which is that this nice consistent picture from the IR that seems to resolve the information paradox and seems to all be self-consistent is in sharp contradiction with other things that we know sort of from the ultraviolet, from string theory in particular. Is that ADS-CFT, where I mean really the strong version of ADS-CFT that says this particular CFT has a dual description in terms of this particular sort of string propagating on this sort of asymptotics, this sort of space-time. These specific string theory dualities, n equals 4 and type 2b on ADS5 cross S5, these sorts of very specific dualities do not seem to leave room for superselection sectors. So I will leave you all with a question. I should probably invite questions from you after this, but I have a question for everyone that I really want to know the answer to, which is how do we resolve this this tension? And I for one, I'm going to be paying very close attention to Samir's lectures because I think that there's a chance to make some contact here, but with some of the UV aspects of string theory and understand how they play a role here. But I won't speculate any more on that. And hopefully some of you can help me understand how to resolve this tension.
Thank you very much, Henry. I suggest we all thank Henry for carrying us through Wormhole safely and leaving us with this question. So we already had many questions and we're a bit over time. So I suggest people who have to leave can leave now, and maybe now, Henry, if you have some time, we can continue a bit with informal discussion or have some questions. So
yeah, I'd be happy to. And I'll try to keep an eye on the Slack for the next few days as well. So
okay,
if
thanks.
people have questions, then that's also a forum they can just.
So please, if anyone wants to ask a question, go ahead. Shweta?
Well, I will let others ask questions first.
Okay.
Yeah, okay. I mean, my question was your last question, so I don't know. What is the state of the art regarding this last question? I mean, at least in this simple low-dimensional models, you must know more than what you're telling us. So could you?
Yeah. Yes. It's perhaps there was a debate as to whether I should review all the stuff about getting the page curve in the first place, or whether I should go and do some of the newest stuff. But yeah, there's certainly. So we have some specific simple low-dimensional models that really realize this factor-less ensemble, and you can sort of talk about this baby universe Hilbert space and so forth, and realize this in a very concrete way. And there's a strategy at that point to try to creep up on this question. Is because of this realization that the ensemble is not an inherent piece of the theory, but depends on the state of closed universes. You can start off with an ensemble over many, many possibilities, and then you can try to cook up a state of a sort of a different initial state of universes that narrows down the set of possibilities. And as you narrow down that the sort of distribution of alphas, you're getting closer to this factorization. So if you really concentrated on a single alpha, you would have factorization. So there's a question of what happens as you sort of dial the width of the distribution. And yeah, there's it doesn't seem, it seems that something cleverer is happening than the most naive thing. The most naive thing is just to say, okay, these theories just don't allow wormholes. It's a pity because they're doing some nice things for us, not just this page curve, but some other things that make a lot of sense. It would be one possibility, but at least in these toy models, something a little bit clever is happening. Yeah, so one of the things, yeah, how do I want to say this? Yeah, so an interesting thing that happens is that as you narrow down this distribution, that means you have to populate the space of baby universes more and more. So you have to create lots of baby universes to narrow down the distribution. And at some point, the sheer number of baby universes means that their sort of interactions and topology changing processes become important at leading order. So usually they're kind of exponentially suppressed. There's some small effects, but if you have enough baby universes, the sheer combinatorics can overwhelm that, and you end up having to take them into account at leading order. But then there seems to be some other sort of effective description that's taking over. And this is very analogous to what happens in string theory. When you go to strong coupling, you get more and more strings, but there's a collective description of some strings in terms of D-branes. And there's something similar that happens in these toy models in terms of some D-branes for space-time, which is like a boundary condition on which space-time can end, and it's giving you some sort of effective description of these alpha states. So based on those toy models, my best guess here is that something in the UV is giving you the ingredients to create something like a boundary on which space-time can end. And that's quite, this is why I mentioned Samir's lectures. This is quite reminiscent of the sort of fuzzball idea that there's a smooth terminating, space-time smoothly terminating at the horizon. So that is the direction I would be speculating at the moment, but I should emphasize that while this is realized in a very concrete way in some of the toy models, it's still speculation more generally.
Just to see if I understand, you're suggesting that in the normal ADS CFT, you should think that the gravity path integral is being done in this state, one of these eigenstates of a fixed alpha, and then there is no averaging, everything factorized. Is that what you mean?
Yeah, so, well, I think I would say that it's, something very dramatic happens, is that the Hilbert space of closed universes, this thing I called the baby universe Hilbert space, in these examples, if you need factorization, if you want factorization, you need that space to be one-dimensional. So it means that really there's only one state of closed universes, but it's the dynamics is somehow picking out a particular state of closed universes and selecting one. It's yeah, so I wouldn't say it's like there's lots of choices of possible closed universes, but there's implicit in our definition of ADS CFT that actually we've made some particular choice. I think instead that there's some reason in these theories where the dynamics tells us that there really is only one choice. This seems extremely surprising from the semi-classical point of view. Like I can write down closed universes in like type 2b supergravity with, I can create a closed universe sort of semi-classically. But the other thing we're learning from the toy models is the semi-classical picture of the Hilbert space is not necessarily actually useful. The full Hilbert space, once you include topology change, can be much smaller. You end up with this sort of null states. So you have things like, you might have relationships where you have some no boundary state plus some other single boundary state plus some two boundary state plus etc. And all of these things look like they're semi-classically entirely different states with different numbers of universes, and they look reasonable semi-classical things that are all distinct. But in the full Hilbert space, this state turns out to have zero norm. And so it's giving you some kind of topology changes, giving you some kind of relationship between states. That's very surprising. And this example where you have a single alpha state is like an extreme example of that, where you have the topology changes doing so much for you that that it gets rid of almost the whole Hilbert space. Yeah. it would take another hour to flesh out those things. So I'm sorry if it's a little bit sort of too quick.
Yeah.
We have a question from Irina.
Yes, thank you for the explanation, Henry. It was very nice. I was wondering, just the last thing you said, like this possible solution, taking into account some brain where the world ends. It reminds me to these bubbles of nothing, which also the brain ends, which in principle should exist, no, if the cobordism group is 0, so that everything belongs to the trivial class. And that also, I mean, the fact that everything belongs to the trivial class is also related to having no global symmetries and having no free parameters, and is what Baffa and McNamara used to conjecture for having a one-dimensional space for the alpha bubble. So do you know if these brains of the world, I mean, this end of the world brains are related to this bubble of nothing somehow?
I'm really sort of out of my depth and speculating already with it. So it is the sort of picture I have in mind, but there's a sort of vast distance at the moment between these toy models where we understand what these end of the world brains look like, and sort of actual, 10-dimensional string theory. So
what is the best
yeah.
You have these end of the world brains?
So in these toy models, there's in these toy models, for example, in JT Gravity, these are called these eigenbrains. Is, well, what do I want to say? Is yeah, so it's just, in that context, there's a two-dimensional space-time, and the definition of the eigenbrains is roughly that you have the space-time can just terminate on a geodesic circle of some fixed length, say. So you can say you're allowed to insert a boundary, and you sum over all possible instances of that boundary. So it's like having a Dirichlet boundary condition for a string, like ending on a D brain, and that does the job of, say, fixing. You've got a dual quantum mechanics, and inserting one particular type of brain fixes a single eigenvalue of the dual theory. So in that instance, they don't really look like the bubbles of nothing, but the speculation, at least, is that perhaps this is like a too simplistic description, and in the full theory, that very sort of abrupt, sharp, you just end space-time is replaced with some smooth capping off. But really, it's speculation, and there's a big gap between the toy models and the full theory.
Okay, interesting.
I could probably speculate more wildly, but perhaps not on this place where I'm being recorded.
Well, Henry, I suggest you can speculate as wildly as you want, but then just let us know where to cut the video before we post it. So. Okay, sorry. I guess, guys, you had questions, so continue.
Okay, can I ask one question? So about your explanation about this page curve using this super selection sector, for that, it seems to me like you just need some kind of like a superposition, P alpha for states, ensemble of states rather than ensemble of theories. Do you really need some ensemble of theories?
Yeah, so the important thing is that is that you get this sort of superposition, right? Is that it's not like, in some sense it's an entangled state, but there's something. So it's not like usually when we have like an Einstein-Rosen bridge, we might think of, like, you could create that maybe by pair producing some black holes, and then you generate quantum entanglement, and then you can pull them far apart. The strange thing that's happening here is that I'm creating black holes in totally different parts of the universe, and yet somehow they're being correlated. And so it's
Right.
so it's of a slightly different nature. But I mean, yeah, and there's like it's not just entanglement within the states. There's some sort of third system, if you like, that's mediating the entanglement, and that's the system.
Yeah, it's a weird, like a classical ensemble of states. But I was just wondering, like, if it's just some like a summation over the states, then like you could in principle get alpha even for like n equals 4 super males versus type 2b string. Although like the way you do computation is a bit weird because like you treat this alpha as a kind of like a classical variable. So.
Yeah, I don't know precisely what you had in mind for n equals 4, say, but yeah. I mean, yeah, this what do I want to say? Yeah, like in the ADS-CFT context, if you have a specific dual, then you can really define these rho alphas as, you know, you use a boundary condition like this, and if you really assume that this is some CFT amplitude, then if this is really, if you can replace the bulk with some, you know, quantum field theory here, then, and use the locality of the quantum field theory, it does not allow for this. So
yeah, okay.
You could put it in by hand in other ways, but and you know, okay, so there's room for these replica wormholes to be absolutely correct if you put in some averaging by hand. The hard question is whether they make sense if you don't put in averaging in by hand.
Can I ask a question about this last point? So for instance, in this work, like the one by the group of Rob, etc., they well, maybe also previous work. I'm not sure that I don't know all of it, but you get both. You get saturation of the entropy, for instance, just by Ryuta Kayanagi in this double holographic pictures, and then that Ryuta Kayanagi would be exactly what you would do if you wanted to compute, at least it seems, if you wanted to compute the von Neumann entropy. I mean, that's just the usual prescription for the radiation, and it would look to me more like the first computation you did, the one in which naively you just computed the Hawking radiation from that. So why is in that case in which there's no, I mean, you forget about you take the gravitational system we were talking about, it becomes just a brain, so you sort of forget about it and you do Ryuta Kayanagi, and then the surface ends on the brain and we're done. So why no baby universes are coming about there? How are they hidden?
Yeah. The answer is that the question you have to ask is where Ryuta Kayanagi comes from, and you have to look inside the box, and inside the box you still have this. It's our understanding of Ryuta Kayanagi from the gravitational point of view is based on replica calculations, and where the Ryuta Kayanagi surface is the branching surface for joining different copies, and even those examples, and unless I've missed something, there are still spacetime wormholes in this definition.
But so you're saying, can I ask more like how if you just look at the computation, if I understand more or less what they're doing, they're like in this double holography, they're just looking for the usual minimal surface, and it can hand on the brain or not, because the brain has some, I mean, it has some action that contributes to it. And so it would look like, yeah, so I'm not sure. So the point is that if I did the replica, okay, I see. So if I did the replica calculation, the fact that the Ryuta Kayanagi surface ends on the brain would mean that there is some wormhole on the brain. So that's the point.
Yes. Yes, that's
okay.
Yeah. Let's see if there's. Yeah, so I mean, one way of saying it is that there's a rule you can use to exclude wormholes, which is that you you take your gravitational space-time and you assign a label to it. You can you assign some discrete label that you demand is locally constant, and you fix it on boundaries. So that's when I okay, I can't remember where it is. I drew some picture with blue spacetimes and pink spacetimes. Here it is. But yeah, this is a principled. It's slightly stupid, but it's a principled way of avoiding replica wormholes. And I think you discover in those examples that by assigning different labels to different boundaries, you would not allow these islands that end, RT surfaces that end on the island.
I see. Okay.
So it's still there under the. It obscures it slightly more probably, but it's still there under the hood, I think.
Let's be realistic, right?
Any more questions?
Can I actually follow up on Marco's question? So yeah, maybe I'm just not understanding, but so in what Marco was saying, in that setup, it's just like a CFT with a boundary, right? Am I understanding right? So in that case, where is the classical correlation that you're talking about?
Marco, you're talking about the sort of double holography setup?
Yeah. So essentially, I'm thinking about what Shot is saying. Like there is either a CFT with a boundary, or in the holographic part, there is some ADS with the end of the word brain that ends on the boundary of the ADS part. And so the Ryota-Kanagi surface lives in this holographic space, but from the dual point of view, it's just a CFT with a boundary, as Shot is saying.
Yeah.
So local, so that maybe helps, but yeah. So I'm also still.
Yeah. So I can't find the right place in my notes, but yeah, from the dual point of view, then yes, it looks like there's no ensemble, but that's because by passing to this dual point of view and assuming it's a unique quantum system, you're sort of assuming away the thing that gravity, at least if you take gravity seriously, it does not seem to allow for that.
Right, but then the question was, why do we still get the right page curve, right? If we're doing something, if that does, so I guess your first answer seemed to say that they're not doing something wrong, that it's just that it's encoded somehow in what they're doing. But if you said we're doing something wrong, we're assuming away the existence of the correlation, why do we get the saturation? I mean, I don't like.
So yeah, I think if they made, yeah. So okay, I think what you have to explain in that context is that there are two rules that both look perfectly sensible for computing the entropy. One of which says you don't allow wormholes, and one of which says you do allow wormholes, and they're getting different answers. That's what you'd have to.
Okay, so you're saying that also in that case there is some. Okay, maybe. Yeah, they don't seem to say there are two answers. They seem to say that they find the right one. But,
yes.
Yeah, somewhere in the detail.
You pick the one you like.
But in practice, so what you're saying is that there should be more than one solution for the minimum for the Ryota-Kanagi prescription in that case. Or I mean, how would I see that there are two possible solutions and you need to the wrong one doesn't lead to the right answer?
I think having this extra holography and so forth is just a way of doing the calculation and the matter theory. It doesn't actually change the basic picture. And it's just okay, I can never find it right. This wasn't the page I was looking for. Never mind. What do I want to say? Yeah, having this third direction, I think, is certainly useful for doing calculations. It means you don't have to go around computing entropies, but it doesn't actually change what's going on. And in that case, there's a question of what rules you use to calculate, whether you allow different, I guess they call them Planck branes, whether you allow Planck branes that end on different boundaries to connect or not. And that's the question of whether you allow for replica wormholes. And from the point of view of taking ADS-CFT with unique joules seriously, there should be two ways to do the calculation and both should be fine. You allow them to connect or you don't allow them to connect and you have to get the same answer. And one of them gets the right answer and is great and we think it's giving us insight, but one of them doesn't, and that's still the puzzle. And one way of resolving that puzzle is to say the original idea of duality was wrong and there's ensemble secretly, or there's some kind of ensemble duality. That's one way to resolve it. It seems clear that it's not the only way to resolve it. So there's some other resolution. But
okay, thanks.
Yeah. I'm not sure I've answered to your satisfaction.
Well, maybe we can also continue this discussion on Slack. It would be interesting if some. Yeah. Okay, let me stop the recording.